Good morning, Year 13s. How's it going, guys? Ben smashed it out the park, being first in like, I don't know, 40 minutes early or something. I think he's literally been waiting on my channel. It's been hilarious. Nikita and Michaela are here. So is Ivan, doing great on there. Nikita, Ivan, Michaela's, Mika's here. That's great. Anyone else yet? Missing Dat, which is unusual. That's usually in by now. Is my sound okay? Anyone else? There we go. The sound's absolutely fine. Tenzi's in the house. I like it. Doing well. I'm missing Donna, Jasmine, and Dat. That's it. Ah, there's Jasmine. Amazing. Jasmine's in the house. So today, guys, we're going to be going through the homework and doing Sn1 and Sn2. That is our lesson for today. Looking at some organics. Do you know what? I'm actually really glad that I'm doing organics today. It's so easy to forget it. And it's like the hardest bit of chem, to be fair. It's also the bit that you can actually do the best on, because once you understand it, you can kind of build everything. It makes everything so much easier. But it does take a little bit of practice, and some people don't like it. Dat and Donna, that's all I'm waiting for. Okay, I'll mark them as missing, I think, and I will crack on. I think that's a good idea, isn't it? Let's just do that. No Dat, no Donna. Okay. Right, let's get a move on. Oh, there's Donna. She's in. All right. Donna, I'll mark you in on the register. Fab. Right. Let's share my screen. Let's get on with this. Let's get on with this. Still need to buy myself get myself a webcam. Desperately need to get myself a webcam. Just so that I can have my face there and I can talk to you guys and wave at you and, you know, all that stuff whilst giving my lessons. You know, it seems very reasonable. Right. So you guys had homeworks. Okay, so on the chat, please, there's Dat, rocking up 5 minutes late. All right, 2 minutes late. Has everyone managed to get through the homework? It was a really quick homework, this one, folks. This is kind of an understand or not. Yeah, so I'm hoping that everyone's finished it, because it should have taken you all of 5 minutes. Yeah, because if you understood the previous lesson, which was a mess, I apologize. They can't all be amazing. If you understood it, then you'll have just finished it. Yeah, it won't have taken you more than 5 minutes to do. Nikita, yes, well done. Emma, yep. Dat, yes, well done. I've got 3 people so far out the 11. Come on, guys. Who else has done it? Has everyone managed to get this done? Okay, I'm going to go through it. Mark your answers. So it's out of 8. It's out of 8. Quite like that. Nice and straightforward. Oh, I've got loads of stuff on my tablet. There you go. Out of 8. Yes. Ben just gives me a smiley face. Ben does. Oh, of course. Oh, OFC, of course. Cool. So first one, we've got the overall reaction. We've got the rate equation. We've got the mechanism. Step 1, step 2. Which one is RDS? And the answer is step 1 is RDS. Tick it if you got it right. 1 mark. Next, nice and easy. And by the way, let me explain it. The reason why is because in the rate equation, there are 2 B's. Yeah. Therefore, in the rate determining step, there will be 2 B's as reactants. And they're there. They are in the same ratio as is found in the rate equation. Nice and easy. Next. So the rate equation states I need 1 E and 2 F's in the rate determining step. Well, in equation 1, I've got 1 E and 1 F. Well, that doesn't fit. I haven't got enough F's. The next one, E and F is there. So step 2 is RDS. And the reason being, the reactants are found in the same ratio that are found in the rate equation. I like it. That looks like KDS. Let's change that to RDS. The rate determining step. Next, J and H plus, RDS step 1. This is easy. Should have taken you all of 6 seconds. Yeah. Next, M2 to the power 1. Okay, the 2 doesn't really freak us out in any way, shape, or form. So RDS. Yeah, nice and straightforward. So that's 2, 3, 4. This should have taken you 5 minutes. Right. only one of any difficulty. Yeah, so RDS is step 2. The reason being is I need 2 A's and 1 C. Well, in equation 1, I've got 2 A's, but there's no C, so that can't be the answer. But those 2 A's become a B. So a B is equal to 2 A's. So I could sub in that for 2 A's. And there's our RDS, 2 A's and a C. Yeah, so nice, that makes sense. Yeah, step 2, because B is an A, 2 A's, and therefore 2 A's and a C gives me my rate equation in their correct ratios. I like it. 5 marks in 5 seconds. That should have taken you all of like 2 secs. This one's a bit more challenging. What they've now done is given you 2 possible mechanisms, stated which of the steps is RDS, and you've got to look at the rate equation and determine if any of these are possible. Yeah? Okay, so we've got possible mechanism number 1, and the rate equation has 1p in it. So straight off the bat, possibility of 1 is not, it can't be. The reason being, if they're telling us that this is RDS, yeah, then Q would be appearing in the rate equation, and it doesn't. So that can't be the case. Next, okay, next, exactly the same thing. Yeah, we have got, they're telling us step 2 is RDS. Well, this would be 2 Q's. If we were going to look at that as an RDS, there would be 2 Q's up here, yeah, to the power of 2, which aren't. So that one's not possible either. So in 6, neither of these suggested mechanisms, no. Yeah, neither of these mechanisms could be correct for that one. Question number 7. Right, possibility for number 1, let's have a look. So it says, I need to have an X and a Y in RDS. Okay, and they're telling us this is rate determining. Okay, so annoyingly, this one is possible. I'll explain why. The reason being is because they've said that X should be in the equation, and we're realizing that X is going through thermal decomposition to produce both A and B is escaping. B is a waste product, yeah, from step number 1. But X is in a 1-to-1 ratio with A. So what that means is, because because it's a thermal decomposition, 1 reactant producing 2 products. Yeah, these 2 are only directly related. These are directly proportional to X, and in a 1-to-1 mole ratio. What that means is you could sub in X into that equation in terms of the concentration of X and A will be the same. So that is plausible, because A is the concentration of A. The concentration of A is directly proportional to the concentration of X. So we could say that because they are the same, yeah, because it's a thermal decomposition and it's a 1-to-1, the concentration of A is respective of X's concentration. So RDS for that is correct. That's the nightmare for that one. Yeah, I hope that makes a bit more sense, guys. That was the hard one. What does this equation now make sense? So this one has got X and Q, right? So Q should be appearing in the rate determining step. Sorry, it is in RDS, but it should be appearing in that. And Q cannot be related directly to Y. So in that case, this one is not possible. So mechanism 1 could be true. Yeah, next. So 1 is a yes and 2 is a no. Okay, last one. So rate equals K, C to the power of 2, D to the power of 1. RDS being step 2. So E is a C and a D. So we could replace that with a C and a D, which would give us 2 C's and a D on that side of the equation. That is possible. Yeah, so that is possible, because the E is representative of a C and a D. Okay, next one. Again, RDS. 2 C's. Now, C2 itself wouldn't have worked, but because of the previous equation, it does. 2 C's is a C to the lowercase 2. Yeah, so that could be replaced with 2 C's, which also gives us the same ratio as in the rate equation. So that one is also possible. Right, so it's a total marks. Now, what I'd probably say is, I think I'm going to make it out of more marks here, because I think each one of these processes is valid. So I'm going to say that it's going to be out of 12. No, it's not out of 12, is it? 1, 2, 3, 4, 5. It's out of 11. Yeah, the marks come from 1 for each of those RDSs and 1 for each of these being correct. Yeah, so, you know, the cross, 2 crosses at the top, a tick and a cross, and then a tick, tick. I think that's very reasonable. Out of 11. Guys, can you fill in your data, please? That would be wonderful. Let's go to the data sheet. Data. Let's have a look on my data. Let's go to my data. Oh, no, I've gone Yorkshire. Oh, no. I don't know why either. Let's go to data. Where's my data? Out of 11. Think that's very reasonable. Shouldn't have taken you more than 10 minutes. How long been on now? Been on YouTube for, I don't know, laptop says sometime. Doesn't actually tell me. I starred this now. Started to figure out how to star stuff. A2 homeworks tracking sheet. I think it's that one. Boom. Love it. Love it. Love it. Winkit hasn't filled in any of his data. Thanks, Winkit. Getting there. Data's going in. 11 out of 11 for Dat. Kayun, 11 out of 11. Emma, 11 out of 11. Wow, that's Ivan, 111. That's amazing. Well impressed. So this is, I'm just going to put RDS as the title in there. RDS. I'll do it RDS 1. I've got another rate determining homework, which I probably think is a bit harder than that. But I'm really, really happy with what we've done on that, folks. I think that's a very reasonable output. It's good. Right. I'm going to shrink that column since I can. Or maybe I can't. Yeah, come on, move. Yes. I want to move it further. Yeah, that's better. Winner. I like it. Look at that. Nearly a full house on all the homeworks. Come on, Nikita. Come on, Tenzi. Come on. Come on. Ben. Has Ben gone AWOL? Where's Ben? Ben, I can't find the doc. Oh, that might be why, Ben. I'll share it with you. Didn't look at the chat and then I suddenly saw it. That's really funny. Ben, you haven't filled in any of your data. I love it. There you go, Ben. Go. Can edit. Love it. Oh, Ben, you've got 3 bits of data to fill in. You might have shared it to the wrong Ben email address. Totally possible. Totally possible. Ben, fill in the data retrospectively. Absolutely fine. You need to do kinetics 1 and kinetics 2. Otherwise, yeah, that's fine though. Right. Today's lesson is organics. Love it. I'm loving it. Right. So we are doing, I'm going to change to black. I'm going to zoom in as well, I think. Yeah. There we go. So organics, and I'm going to put in brackets nucleophilic substitution. Nucleophilic sub. Now, can I just point out, you're not allowed to shortcut any of those words in your exam. Yeah, you must fill it in. You have to write nucleophilic substitution. Yeah, you can't shortcut anything. That's really important. You got to. I've seen people put nuke sub before in an exam. It's definitely not allowed. Yeah, definitely. Okay, so we've been looking at nuke sub before. We've done all of the. We've done this mechanism, and we like it. This one's okay. The problem is we didn't go all the way, because what I need to do is I now need to talk to you about it in a little bit more depth. And please don't feel like I've lied to you. I haven't. But in AS, they're just trying to get the basic understanding, of understanding that organic mechanisms and how they go about, and the making and breaking of bonds, the understanding of how curly arrows are arranged, the importance of deltas. And now what we do is we look at it from a kinetics standpoint, because it turns out that there's 2 nuke subs. There is Sn1 and Sn2. And what this stands for is substitution, nucleophilic, it's telling you attacker, nucleophilic, and the one tells you one species in RDS, in the rate determining step. Only one species. So SN2, I think everyone's going to go, oh, okay, there's just going to be two species in the rate determining step. And that is correct. Yeah, this is not complicated. This is still nucleophilic sub. Yeah, this is substitution. It is with a nucleophile. Yeah, nucleophilic. And there are two species in RDS, in the rate determining step. Okay, so let's look at what we remember about nuke sub, and let's keep it easy. Let's keep it simple. Let's go for the most basic nuke sub. Basic. Can anyone guess what my nucleophile is going to be if it's a basic mechanism? Oh, it's a terrible chemistry joke. It's so bad. What's my nucleophile if we're doing the basic mechanism? Come on, guys. Don't let me down. Emma, legend. Good job. Ivan, if you're going to put O, yeah, can you at least put O capital H minus, please? Thank you. Emma, absolutely right. Well done, Dana. Well done, Nikita. Nikita, can you capitalize your O and the H's in future, please? Being really picky there. So we're going to do nuke sub with sodium hydroxide. So this is what I'm now going to do is I'm going to do AS nuke sub. Yeah. And going to keep it super simple. Yeah, super simple. Chloromethane. Yeah, plus OH manas. This is our reactive species. Yeah, reactive spec. The reagent, yeah, NaOH is the reagent. Remember, the word reagent means title on the bottle. The sodium ion is just a spectator. Yeah, reagent and reactive species. Step 1, find your delta. Step 2, curly arrow from the middle. I'm going to color code my curly arrow. Curly arrow from the middle of the lone pair. Curly arrow to break the bond. Look how I've touched it. Yeah, look at that. Really important focus. I have touched that bond. Yeah, I'm feeling up the bond, guys. It's important. There we go. And it's all over. That's what you guys learn at AS nuke sub. Except with ammonia, which is 2-step. Yeah, except with ammonia. And our product, of course... Our product is methanol. Yeah, there's our methanol product. And we're going to have sodium chloride as a byproduct. The chloride ion floating around. But the Na plus, of course, is also floating around as well. But so byproduct, not that it really matters. Okay. So, I didn't lie. I just haven't talked to you about the kinetic side of things. There's a bit more detail. So what we now need to do is, we now need to recognize this Sn1 and Sn2. So what we realize is, what we're going to do is, I need to do this as a thought experiment, right? So Sn1 versus Sn2. We recognize that the class, underline, the class of haloalkane, we recognize that the class of haloalkane affects the rate of substitution. The rate of substitution. And I'm going to put full stop. I'll put in We know this. This is the important bit. Yeah, well, it's not the important bit, but just the nota bene. We know this because of the silver nitrate. We did an experiment, and they love to ask about it, folks. Yeah, an experiment of silver nitrate aqueous. Yeah, silver nitrate aqueous and haloalkanes. That's what we were doing. We did an experiment with these. Yeah, I'm going to put that, I'm going to circle that in red. Just so you know, I like putting nota benes in spangly boxes. They do like to ask about this. So, and just to let you know, let's draw this out and explain what's going on in that experiment. Yeah, we had a we did all of them. Okay, I'm gonna have to do all of them, aren't I? Right, okay, so we had, I think we actually had, like, it was butane, I think. Yeah, I think that was actually the one that we had. I'll do this legitimately, I guess. Yeah, I'll arrange it as best I can to make it easy to understand. Yeah, C3H. Oh no. Let's do that. H 4 7 7. There we go. So that's one chlorobutane. Yeah, primary. Yeah. Primary halo. Primary halo. Then we have C2H5, put the H there, and then I'll add a little CH3 here. Oh, maybe I'll put that off to that side to make this kind of, the problem is if you do that, flipping it around, often students struggle with that. This is a secondary halo. This is 2-chlorobutane. Yeah, if you want the names, 1-chlorobutane. Yeah, it's nice to do the naming as well. Yeah, this is 2-chlorobutane. Yeah, and then I'm going to put onto the chat. Let's put onto the chat. We then did this one. I'm going to ask Ben, can you name this for me? Can somebody name that for me? It's a tertiary halo. Wonder how long that will take to appear on the chat. I'm just going to move that a little bit over if I can, if it lets me. There we go. That's okay. Got it. There we go. And what we did is we did this with silver nitrate aqueous. Now, the tricky part of this was we did all of these three with silver nitrate aqueous. Now, the question is, why did we do that? Yeah, the reason why is because in reality, the silver nitrate is not the actual attacking species. The attacking species is the aqueous. It's the water that's going to act as the nucleophile. Yeah, so what happens is the H2O, yeah, the H2O comes along. It's a weak nucleophile. Yeah, and it's going to kick the chlorine off. Yeah, and it's going to do it for all of them. 2-chloro-2-methylpropane. Thank you, Ben. You star. What a legend. Even in alphabetical order as well. Superb, Ben. 2-chloro-2-methyl. Thank you, Ben. Really, really impressed with you there. 2-methylpropane. Perfect. Great job. Okay. And so the water kicks all these off. Now, the problem is there's more to this than that. We know that it turns out we would expect from the delta perspective, yeah, from a delta perspective, let's put on the whole point of primary, secondary, and tertiary is this, because the deltas are scaled in size. Yeah, here's the delta on the primary, here's the delta on the secondary, it's reduced. Yeah, and here's the delta on the tertiary. It's tiny. And this is due to the positive inductive effect. Yeah. Yeah, this is due to the pi effect. Yeah. Reduction in polarity, brackets CCl bond, due to positive inductive effect. Due to positive inductive effect, otherwise known as pi. Yeah, the pi effect. I often just shortcut this, and that is so important, that one. The positive inductive effect, otherwise shortened to the pi effect. Yeah, it's just an easier way to remember it. Positive inductive effect. So what we would expect here, we would expect the primary to be the fastest reacting. It turns out it's not. Now that's weird. It should be, because the nucleophile is water. The nucleophile is also polar. We know this. Yeah. So the slightly negative O is going to be attracted to the slightly positive carbon on the other one. So we would expect that attraction to be greater on the primary. But the strange thing is the tertiaries react faster. Yeah. In terms of rates, the tertiaries are quickest. That seems very strange. There's something odd going on here. The reason why is they're going through different mechanisms. Okay, so here's the real ones. So, primary halos. So a primary halo goes through an Sn2. So primary halo alkane, I'll actually be good and actually write alkane, go through Sn2. Just to let you know, the N is actually subscript. Yeah, it's actually like the numbers are in H2O. Yeah, it's subscript in reality. So it goes through an Sn2. Now remember, we know what nuke sub is. That's easy. But this says 2 species in rate in RDS, rate determining step. So what are they? Here's now a true Sn1. And you're not going to like this, folks, because there's this really bizarre bit that people go, oh, I don't like this. So let's go for a primary. Let's just go for chloromethane. Yeah, let's keep it simple. Right. And this does exactly as it was before. Yeah. So the question is, why is this? So there we go. There's my first step. There's the mechanism you guys all know and love. However, because we now pick this up at A2, we now get what's called an intermediary. Intermediate. No, I won't. There is an intermediate bracket transitional intermediate state. Yeah, transitional literally means we're moving through it. Yeah, we get an intermediate. I know that's a bit of a nightmare. I've no idea why it didn't let me take my tea. There we go. We get an intermediate state. And here's what I need to make sure I've got enough space for this. Do you know what I'm going to do? I'm going to move that sign. Yeah, I'm going to move that to below. Yeah, so I can give myself more space. I've lost that T again. Come here, you. There we go. Intermediate transitional state. What does it look like? It looks like this. Now, this is the nightmare, folks. Yeah, this is the nightmare. Bear with me. C. Right, now here's the thing. This original step now needs editing. Yeah, that original step now needs a slight bit of editing. Because it turns out that during an Sn2, you actually form a trigonal bipyramidal transient state. Which looks like this. Yes, the carbon now has 5 bonds, and it does not like it. Yeah, so you actually get this transient state, and the full thing is now actually fully negative in reality. It is actually fully negative. Not that they usually care about the square brackets and the charge. Yeah, but this is now nukes. Can I just point out, they're still going to ask you for the normal AS one, but they will also ask you for this because this is the step to A2. Yeah, so it becomes that. And now we get our normal everyday product that we know and love. Yeah. So, and now the OH is there. There we go. And the Cl's left. So we started this original molecule here. Should have drawn it all spatially. Should have. Not that it matters. This molecule here, I'll do this in red. This molecule here was tetrahedral. Tetrahedral. Yeah. It becomes trigonal bipyramidal. Trigonal bipyramidal. Trigonal bipyramidal. Bipyramidal. There you go. And then it drops back in to being tetrahedral at the end again as well. Tetrahedral. So, and that is much harder. You notice the conservation of charge through every step. Yeah, we've got, if we actually just split this up, yeah, split. At every stage, the conservation of charge is true. This side is still 1- because we've got a neutral chloromethane and a fully negative OH-. We've got a fully minus transitional intermediate, and then we've got the Cl- giving us the conservation of electric charge at the end as well. Cool, that. Great chemistry. And before anyone throws on the chat, yes, you need to draw it in the trigonal bipyramidal state. Yes, you are needed to have to show the wedges and the dots for the bottom one. Sorry about that, folks. Doesn't really matter where you put anything. Yeah, it doesn't really matter. They won't care about that. But there is Sn2. Why does it have a transitional state? Oh, that is a really good question. Okay, so Emma, the reason being is when the transitional state is a real thing because we can detect it. We can't capture it, but we can see it transiently. Yeah, if you look at this spectroscopically, yeah, each of these molecules have a different absorption of, let's say, visible light or infrared. Yeah, so if you actually do this, if you actually have this, imagine this is your beaker, your cuvette even. Yeah, this is your cuvette where you're in biology, and you've got your reaction mixture in here, and you're shining in UV light or, yeah, whichever one you want to be measuring it with. Yeah, and you've got your detector then picking out what comes out on the other side. So here's our detector. In the graph, we see a rather interesting one because essentially you see a graph that kind of does this. It's continuous as well. You see this. Actually more like this. You see that? That's the graph you see. And what they realized is that graph is strange because if this was going through without the intermediate, yeah, you would just get this here. If you then mark each of these points, so this is just, by the way, this is just time, yeah, but this is absorption. Yeah, and what they realize is that level there, that absorption number is for the original primary halo. Yeah, that's what it's for. And this one here is for the methanol at the end point. So they can see the absorption, but what's this? That is a very unusual thing that we shouldn't really see it. We should have, what they were expecting to see was that. Yeah, this just nice, easy slope on through, but we don't. There was a transitional state which is unstable. How is it carbon can suddenly make 5 bonds? Do the orbitals fuse or something? Rhea, hybridization, yes. Yeah, there is a transitional hybrid state. To make the 5, it's probably, I could probably build it for you if you want. And that transitional state there is for the, shouldn't do that. Make it a bit neater. There we go. For the 5 bond transitional bit. Yeah, and then these are just H's. Doesn't matter where you put anything. So We see it spectroscopically. You can't capture it. So Ria's now asked, how does that suddenly make 5 bonds? Eek. Okay. Orbital pictures. So we've got the 1s. There's the 2s. There's the 2p. Then we've got the 3s. Then the 3p. And then the 3d. And then the 4s. I'm just going to draw that out. There we go. So carbon's original, you would expect carbon to actually look, because carbon's only got 6 electrons. Yeah, carbon has 6 electrons. So if we put carbon's electrons on, I need to make this color so it's easily seeable. You would expect it to be like this. Yeah, that's what you'd expect from carbon. But in fact, it's actually not. Lol. It is as an atom, by the way. As an atom, yeah, by the way, those numbers there are from the periodic table. Yeah. So as an element, yeah, on its own, as a singular atom, that is what it would be, but you can't ever get a single atom of carbon. Yeah. What in fact happens is you find it in the form of diamond and graphite. Yeah. Graphite's a bit more complicated. Let's just look at it from a diamond perspective. Yeah, we know that carbon forms 4 bonds in diamond in a tetrahedral arrangement. Yeah. There we go. So it promotes one up to here. Yeah. And that now forms a hybrid. Yeah. A hybrid there. That's awkward, isn't it? Now, what now happens is, can you see that we've got an empty orbital just up out the way? Yeah, the 3s. And it's empty. Yeah, we now have this scenario, by the way. This is the new scenario for diamond. Yeah, it can now make 4 bonds. Hybrid, this is an S. An sp3 hybrid. Yeah, hybrid. It's fused. The reason why it's sp3 is because there is one s orbital, one s orb. Yeah, suddenly realizing my pen's too thick. This is one s orbital. Yeah, and 3 p orbitals fused together, sp3. Yeah, and when you form the transitional state, look what now happens. What kind, impress me year 13s, what kind of a bond is about to be made in that scenario? What bond? Uh-oh. Oh, I don't like it when it does that. Okay, it's okay. It's all right, we're okay. What kind of bond is about to get made here, folks? First person on the chat, please. Ah! What? I didn't scream like a girl. What bond is about to be made there? Come on. On the chat. Come on, come on, come on. Who's going to be in first? It's only about a 40-second delay. Dative, that's in there. He knows it. Ivan, well done. No question mark needed. Solid. Is it a dative? Yes, it is, Ben. Thank you very much. All 3 boys. Well done, guys. Really impressed. So it's going to form a dative. What that means is for this to form a dative bond, it's going to need to have a completely empty orbital. And guess which one it's going to steal? So what's now going to happen is this orbital here is now going to get fused. Temporarily, very unstable. Yeah, very unstable, but it will do it temporarily. And it will form a beautiful S2P3 hybrid. Yeah, of 5. Yeah, and that now can, and it's going to, carbon now looks like this. Yeah, and it now forms that dative. People often say, where did the energy come from the fusing? From the making of the covalent bond in that step. The making, mexobendo, making bonds is exothermic. Yeah, it's not stable. Yeah, it doesn't want that even though the energy has been supplied to do it, it's not going to want to stay there. It's in an uncomfortably high energy state. Yeah, but that's cool though, right? An S2P3 hybrid, very unusual that. Very unusual. So we form this transitional state in Sn2. So here's now the thing. Sn2. Why the 2? 2 species in RDS. And here's the thing. And I just need to highlight it. This step. We realize here that this here is the slow step. This one here is RDS. Step number 1. The decomposition, step 2, this step here, step 2, is going to be really fast. Yeah, step 2, because you're going from very unstable, yeah, very unstable to stable. Yeah, that step is going to be really quick. But the first one is going to be slow because it's going from stable to, or relatively stable, yeah, compared to the intermediate, to unstable. Yeah, that's RDS. And there's 2 people in it. Yeah. So the important thing here is to recognize that, and this is a big fat nota bene. Yeah. Sn2. The concentration. Oh no, don't do this to me, tablet. The concentration. I'm gonna quickly just close this and then reopen it. I'm really hoping it's gonna give me enough time just to finish my lesson. I don't know why it's getting fairly erratic at times, this thing. A bit worrying about it. So we've got bullet point number 1. The concentration, the conc of haloalkane and sodium hydroxide are both first order. Rate equals K. Oh, the tablet's going to kill me. K. Primary halo, I'll put halo alk. And I'm even going to put little 1 to the little deal like that. And it's first order. That's just saying primary. I'm going to put pre. Yeah, and it's first order. And OH minus is also first order. 2 species in the rate determining step. Okay. Let's now go to Sn1. I don't know why this is showing me that. It shouldn't be. Go away. Okay. So we've just done Sn2, which is strange. People think I'm going to do Sn1 first because 1 and then 2, but I don't. Sn, it's subscript, remember? Sn1. Nucleophilic, nuke sub, nuke, 1 species. 1 species in RDS. Right. Now, Sn1 is all about the tertiaries. Yeah. This is the tertiaries. Tertiary halo alk. Yeah. So, why? What's different? I don't like that. I just want to do that. I think it looks better. Tertiary haloalkanes. Do Sn1. What's the difference? The difference is the delta. The delta is getting worse. No! I don't know what's going on. Oh, it's getting worse, folks. Don't know why. The tertiary haloalkanes, right? The tertiaries, due to the pi effect, the positive inductive effect from the carbons, we know what this is. This is the drifting of these electrons. Yeah, carbon allows a little bit of drift. It reduces the delta. Yeah, it reduces the Cl is actually still just as big, annoying. It reduces the delta. Yeah, on that C. What that means is the OH minus can't see it. Yeah, there is very little attraction. It can't see it. Yeah? Question mark. It's got no attacking. So the mechanism is odd because this doesn't actually take place. This doesn't take place in step number 1. Step number 1 is this. This is step 1. Thermal decomposition. Thermal decomp. There we go. Thermal decomposition. Step 1. Step 2. Step 2. Step 2. Final product. 2-methylpropanol. Can't bother with that. My tablet is all of a sudden gone really slow. It's due to its hiccuping. It seems to be okay when I zoom in. That's interesting. So, step 1, step 2. Right, question on the chat. Which one is RDS? Yeah, which one is RDS? Step 1 or step 2? Isn't the first step reversible in equilibrium? That I'm gonna say sure. Yeah, doesn't matter. If it breaks off, the OH minuses are going to jump on. You're going to say that the chlorines could jump on just as likely. Yeah, they could do. You could argue that it's reversible. Yeah, everyone recognizes that step number 1 is the slow one. There's RDS. Yeah, everyone sees it. Shouldn't do that. Stupid. There's RDS. Yeah, it's rate determining. Thermal decomposition is slow. And look at step 2. Step 2 is going to be way fast. Yeah. It's going to be really, really quick. Opposite charges attracting. Yeah. And I think everyone would have got this. If I had said this, A going to B plus and C minus, and then B plus OH minus going to, I don't know, D. Yeah. And said which one's going to be the fast and which one's going to be the slow. Everyone would see this one here as the fast one. Yeah. And therefore, that one must be the slow. Yeah, thermal decompositions are always slow. So, so what's my rate equation? The rate equation, as a result of this, I'm going to get rid of that. I don't actually like it. If I was going to do that, I should have done that as the full equation for what's going on. That actually probably would have had more value. But rate equals K. Tertiary halo alkane. Halo alkane, tertiary. And that's it. The OH minus doesn't appear in the rate in the rate equation. The reason being is it's 0 order. This is just a quick note to Bene. Yeah, OH minus is 0 order. It doesn't matter what concentration I put in because it's going to be waiting for the thermal decomposition of the haloalkane. So it doesn't matter. Makes no difference. Okay. And amazingly, guys, we're done. That's it. Sn1 and Sn2 done with 6 minutes to spare. Woo! Blimey. That was a cool lesson, though. I really enjoyed that. I haven't done the spectroscopic analysis showing the intermediate before either. And I've also never done no one's ever asked me to do the hybridization before either. That was a lovely, lovely lesson. Really enjoyed that. That was a lot of fun. Learning objectives. I didn't give you any. Need you to be able to draw Sn1 and Sn2 reactions showing the intermediate molecule in the Sn2. And you need to be able to recognize, oh, last thing. What about a secondary halo? Last nota bene. Secondaries? Secondary halo? What will they do? On the chat, please. Which one do they do? Sn1 should do its subscript, Mr. Duncan. Should make it clearer that it's subscript. Sn1 or Sn2? I need people to write Sn just so I know the difference between the one above or below or whatever. Guys, I'm so sorry. I've been mean here. Come on. I'm going to let you know, though. Hint. It's a trap. Because the answer... bit of both. Just so you know. They do a bit of both. Right. That's it. My lesson's done. My lesson here is over. Guys, I will see you next lesson. Both, neither, rips. Lol. Yeah, both is the answer. It's a bit of both. Guys, I will see you next lesson. I will set your homework. You've got an Sn1 and Sn2 homework to do for today, for next lesson, which is on Monday. Whoop, whoop. I'll set that on the classroom today, folks. Go and have a nice break time, guys. I'll see you all soon. See you later.